Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and today I'm talking with Mike Jones, Product Line Manager, COTS Digitizers, Aerospace and Defense at Analog Devices. Welcome, Mike.
Thank you. It's good to be here.
So in this episode, we're going to discuss the integration of high-speed digitizer ICs with wideband RF and microwave front ends. So Mike, what are some of the benefits and challenges of direct sampling with high-speed digitizer ICs?
Yeah, thanks for the question. So ADCs and DACs are sampled at a certain sampling frequency, and that frequency impacts the instantaneous bandwidth, which the converter can provide. And so half of the sampling frequency defines the first Nyquist zone, and the width of the Nyquist zone defines the bandwidth the converter can achieve. And so if the analog input bandwidth is large enough, you can inject an RF and microwave frequency in the second or higher order Nyquist zones. However, engineers still had to contend with a Nyquist boundary that was at half the sampling frequency and multiple layers thereof. So the benefits with direct sampling is that with all that background provided for context, high-speed converter sample rates have increased over the last few years. And so this has led to wider Nyquist zones and therefore wider instantaneous bandwidths compared to previous generations. And so now enter direct sampling into the equation, and direct sampling is a technique in which someone can inject an RF and microwave frequency into the ADC, and perhaps still with some amount of gain and filtering in a front end network, but now without the need for historical heterodyne or super heterodyne analog mixing approaches, which downconverted the desired carrier frequency such that it would fit within the first Nyquist zone of the ADC. Therefore, direct sampling offers wide instantaneous bandwidths. Now that we have wide instantaneous bandwidths, we can also leverage the hardened digital signal processing blocks in the high-speed converter ICs to tune the desired bandwidth and the carrier frequency selection in the digital domain. And so this leads to software-defined bandwidths and frequencies of operation, which provide quick configurability and scale to multiple applications using that same hardware. You may have heard the term software-defined radios, software-defined radars, but leveraging that software aspect with the hardware to provide configurability. So in this direct sampling technique, in many ways, it can significantly shrink the footprint of the RF and microwave front-end networks, which historically required local oscillators or LOs and mixing stages to be distributed for all the analog up and down conversion devices required. However, there are some challenges. So although we now have wider bandwidths, the RF and microwave engineer is now faced with a different kind of problem in that the challenges originally posed by mixing stages are replaced now with things such as wide analog bandwidth filtering that's software configurable, achieving broadband gain stages and devices, attaining broadband single-ended to differential conversion devices, as well as realizing for some flat passband responses throughout the wide instantaneous bandwidths needed.
Yeah, there's definitely been some impressive progress made in the bandwidths. So how does direct sampling at historically high microwave frequencies impact the RF and microwave front-end design?
Yeah, so in the past, many converters were not only sampled at low rates, but they also had narrow analog input bandwidths. And so as a result, the engineers historically were forced to mix down in the analog domain to the first Nyquist. And this required the aggregation of many channels to set to different carrier frequencies to reach the desired frequencies of interest in a broadband system. To compound matters, each channel would be forced to contend with the Nyquist boundary that was placed at half the sampling frequency and multiples thereof. Now with the combination of increased sample rates and wide analog input bandwidths, which allow higher order Nyquist sampling, direct sampling can be realized. And with novel high-speed converters, these channels can now instead be software configurable in the digital domain. This arguably simplifies the front-end architectures by removing analog mixing stages and replaces those front ends with smaller footprint designs concentrated on broadband filtering and gain control.
And so are there any chipsets in the industry now which offer a good balance of the wide instantaneous bandwidth along with high dynamic range for the entire transmit and receive signal chain?
Yes, Analog Devices has recently announced its Apollo MXFE chip. Namely, this is the AD9084 and the 9088, which offers 4 DACs at 28 gigasample per second. So think these are 14 gigahertz of Nyquist zone, 4 ADCs at 20 gigasample per second, so a 10 gig Nyquist zone. It also allows for analog input bandwidths up to 18 gigahertz. And so you can direct sample even in the second Nyquist throughout KU band, for instance, without an analog mixing stage. As it relates to the front end networks and sample clock generation type devices, there's also other chips, such as digitally tunable filters in the analog domain. So these would be parts such as ADMV 8818, ADMV 8913, ADMV 8420, as well as broadband amplifiers in the front end, things such as a single-ended broadband amplifiers like the ADL 8100 or the ADL 8102. There's also single-ended to differential amplifiers such as the ADL 6331. Multifunction RFICs are becoming a trend in which you'll combine digital step attenuators and tunable filters and gain stages and even some mixing stages all into a single small one IC itself. And so those are coming out. In addition, now that we're sampling at higher frequencies, we have to have higher PLL VCOs. Clock sources that can clock things like Apollo. And namely, one of those is the ADF 4382A. It's a clock that allows that 20 gigahertz clock to be sent into Apollo, for instance, with just using a low frequency reference input.
And so given that wide variety of ICs, what is an example of a system that integrates a wideband RF and microwave front-end, wideband digitizer IC, embedded hard digital signal processing, and soft fabric?
Yeah. So with ADI having so many different chips in its portfolio, this fact allows us to develop system level solutions that can be created using vertical integration from the diverse product line that we have. And so one example of that is the ADSY1100. This is a 3UVPX microwave tuner plus digitizer plus processor, all within a single 1-inch pitch slot. It's based on the Apollo MXFE as the backbone IC. It includes 4 receive channels, up to 20 gigasample per second ADCs, 4 DACs, up to 28 gigasample per second DACs. Has a tuning bandwidth from 0.1 to 20 gigahertz. The system is partitioned into 2 separate cards within a single 1-inch pitch 3UVPX slot. There's a digitizer base card, which houses Apollo, clock circuitry, FPGAs, MP-SOCs, and then there's a bunch of swappable tuner personality cards that house many of the ADI RF front-end chips for signal conditioning prior to entering the digitizer base card on the bottom. The system's software configurable. Now that we're packing so much into a small spot, we need to make sure it's software configurable. You can provide a single 12-volt rail that derives all the voltages needed for the system using ADI's micromodules and LDO devices. There's multiple swappable tuner personality cards that are developed in the ecosystem. They're intended to mate to that common digitizer base card, so you can have system architects analyze the trade-offs regarding different frequency ranges of interest and other front-end architectures just by swapping the tuner personality cards onto a common digitizer base card. Onboard memory, there's digital offload options in the form of 1 gig Ethernet up to 2x100 optical Ethernet coming off the card, as well as PCIe. So a few options, but leveraging the diverse portfolio within analog devices.
Yeah, that's an impressive amount of performance packed into a small area. Well, thank you, Mike, for talking with me today about the integration of high-speed digitizer ICs with wideband RF and microwave front ends. I know I learned a lot today, so thank you for that. To our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.